Okay, in the last lecture we have derived the second derivative test in terms of this QH, that is the second term in the Taylor series expansion. So, what we have done is this thing, that is for f on an open set R and x naught in U, I have a critical point that is grad f of x naught is 0. Then we have taken q of h with half or without half h prime Hessian f at x naught h. Okay. And what was the test? That QH greater than 0 for all h implies x naught local minimum, QH less than 0 for all h x naught local maximum, and QH1 greater than 0 for some h1 and q of h2 less than 0 for some h2 implies x naught is a saddle. That is what the test was, second derivative test. Now, we also had noticed that in the proof also that we have used mainly the scaling property. So, because of the scaling property, any h can be brought down to norm 1, that there is nothing wrong in assuming instead of for all h norm 1, for all h norm 1 and h1 norm 1 h2 norm 1, right. So, what we can do here is that we can write here again QH is greater than 0 for all h in Rn. This is to same as saying minimum of, let us say, let me write in this form now instead of h, y in Rn norm y equal to 1 y h f x naught, this is greater than 0, this is if and only if. Similarly, QH is less than 0 for all h in Rn, this is if and only if maximum y in Rn norm y equal to 1 y prime h f x naught y is less than 0, and QH1 less than 0 and QH2, the third statement there, greater than 0 if and only if minimum of y in Rn norm y equal to 1 of y prime h y is less than h f x naught y is less than 0, less than maximum y in Rn norm y equal to 1 y prime h f x naught y, right, because this is because of scaling property you can deduce that. So, look at these two both clear at the same point, you will see that what I have written is this just because of the q lambda h is lambda square q h. But why I have written like this? Because you see every time I have to check, I have to compute this q h and see if I want to use this board for checking minimum maximum or saddle point, I have to kind of check for every h. And if I write it in this way, well, I have reduced the problem to norm of y. So, look at this form at norm of y only 1, that is a reduction, but it is not a great reduction. But if you now I apply some results from linear algebra, then this will give us a great advantage in actually checking minima, maxima and saddle point. And what is that? Under the assumption we made that del square f del xi xj, they are continuous at x naught, this h f x naught, under the assumption we have proved that mixed partial derivatives are equal. So, h f x naught is a real symmetric matrix. And what do you know by real symmetric matrix? That they have real eigenvalues and their eigenvectors can be chosen to be real as well. And this quantity has a special meaning here, this quantity has special meaning in terms of eigenvalues. So, if you use your linear algebra, the first course in linear algebra, minimum y in Rn norm y equal to 1 y prime h f x naught y equal to lambda min, the minimum eigenvalue of h f x naught, and the minimum is attained at an eigenvector y corresponding to lambda min, that is h f x naught y equal to lambda min y. Similarly, maximum y prime h f x naught y norm y equal to 1, this is maximum of the lambda max, that is maximum eigenvalue of h f x naught, and the maximum is attained at an eigenvector y corresponding to lambda max, that is h f x naught y equal to lambda max y. This is a simple result from linear algebra, you prove it. This can be verified with calculus as well, and we will be able to do it after the next week when we do it Lagrange multiplier technique. Maybe I will do it or maybe I will give it as the assignment, but for time being let us record linear algebra and this result. So, what it says now here, that if the minimum eigenvalue is greater than 0 and all eigenvalues are greater than 0, then it is a local minimum. If maximum eigenvalue is less than 0, then all eigenvalues has to be less than 0, then it is a local maximum. And if there is some eigenvalue less than 0 and some eigenvalue is bigger than 0, then it is a saddle. So, in terms of eigenvalues, this is the test of second derivative test reduces to this thing, that should looking for the eigenvalues. But in general what happens, that IN values, if n is large, n equal to 2 no problem, n equal to 3 okay, not too much of problem, but n equal to say 100, then calculating the IN values may be a difficult task in general. So, from this observation and this linear algebra result, we will now write down a practical test for actually checking minima, maxima and saddle points in case of non-degenerate critical point, that is when Hessian has non-zero determinant. So, instead of checking QH for every H, we just go through this check and that makes life little easier. Now, if you can calculate the IN values, nothing better. Okay, so let us write it as a theorem. So, again the same setup, f is from open set to R, x naught in U and grad f x naught equal to 0, that is x naught is a critical point. Instead of avoiding writing grad f x naught every time, let me put a notation for it, a equal to, because I am looking at 1 x naught. So, let me write it as A, just say n cross n matrix A. Okay. So, from that this second board whatever we have, I will write down the statement okay. Do not worry, I just want to make it P, because I have to use this notation X in the proof. Okay. So, do not worry, in x naught I will use P instead of point x naught I will use some point P. Okay. So, let H is equal to Hessian and k equal to 1 to n, A k be the kth principal minor, kth principal minor of A. What does it mean? So, A is this n cross n matrix. You look at the 1 by 1, first 1 by 1 matrix, this is A1, the first row, first entry of the first row, first column. Then in the first row you take 2 elements and then second row 2 elements. So, I think you all know what is principal minor. So, this is AK is the A matrix where k plus 1 to n and k plus 1 to n entries of rows and columns are deleted. Okay. So, conclusion is like this: if for some k determinant of A 2 k is negative, okay, not A k, but so k has to be between 1 to n, then P is a saddle. B, if determinant of an is A, so is not equal to 0, then so let determinant of an not equal to 0, the Hessian is non-zero determinant. If for all k determinant of AK is greater than 0, then P is a local minimum. Okay. In fact, I can write it in this form: determinant of AK is greater than 0 for all k if and only if P is a local minimum. Okay. minus 1 power k determinant of a k is greater than 0 for all k, greater than 0 or less than 0, greater than 0 for all k, if and only if p is a local maximum. And finally, if determinant of a n is 0, p is a, we have already called it, degenerate critical point, and in this case the test fails. Okay. Before I prove it, let me give an example of how this test can be applied. So, let us take there are many examples here. Let us take one, okay, x square y square z square z minus 2x. If x example x y z x square y square z square x minus 2x. So, first search for critical point. Correct. Grad f p equal to 0. What is the solution? You will see the only solution is, if you solve this, the only solution is p equal to 1 1 and 1 1 and minus half. I have written something wrong, right? Yeah, sorry. Del f del y is x square plus 2 y z, and del f del z is, I have missed this part, y square plus 2 z x. 2z 2x 2x, no 2 z x, ठीक है. Del f del z is y square plus 2 z x, x square plus 2 y z, y square plus 2 z x, yeah. That will give us this thing. So, let us calculate the Hessian h f at p, which is a in that, which is equal to del square f del x square del square f del x del y del square f del x del z, so on. You calculate how much is that. First column, del square f del x square, that is gives you 2y, del square f del x del y, del x del y, that gives you 2x, and this gives you del f square del z, that is 0. Now, del square f, so I know what will be here. This will be 2x here because symmetric matrix, and here it will be 0 again. Okay. So, del square f del y square, that is 2z del square f del y square 2z, and del square f del z del square f del z del y is just del square f del y del z. So, this quantity is del square f del y del z, which is equal to how much? 2y. So, 2y here it will be, and del square f del z square is equal to simply 2. Is that okay? That at the point P, so which is equal to the matrix 2, 2, 0, 2, minus 1, 2, 0, 2, 2. Okay. And you see determinant of A2, which is this part, is minus 2, minus 6, this is minus 6, less than 0. So, P is a saddle. Okay. So, I do not have to check for Q and all those things. Check the calculation carefully, but okay. Theorem is okay. So, for today I will start the proof because time is running out, and I will complete the proof in the next lecture. Proof is very interesting. So, first the A part. So, let me try if I can finish the proof of A part today. Okay. What I have assumption? So, determinant of A2k is less than 0 for some 2k less than equal to n greater than equal to 2. Okay. So, let me have this point P, critical point. Let me write it as P1, P2, P2k, P2k plus 1, Pn. Okay. Let us take this set V. This is set of all x1, x2, x2k, this set such that x1, x2, x2k, p2k plus 1, pn belongs to U. That is, I take the first 2k section of U with the last 2k plus 1 to n coordinate fixed. Okay. And I define, so this is a subset in R2k. I define G from this V, this is an open set in R2k to R by G of x1, x2k equal to f of x1, x2, x2k, pk plus 1, pn. Okay. Then what I want you to do, so P is this, let Q is this, you calculate Hg at Q. You find out, since Pk plus 1 Pn's are fixed, this is del square f del xi del xj I equal to 1 to k, j equal to 1 to k, which is a to k. So, now what do? I know determinant of a to k is given to be negative, but what is determinant of a to k? A to k is a real symmetric matrix. So, let beta 1, beta 2, beta 2k are eigenvalues of A2k, and then all of you know this result, determinant of a matrix symmetric, if I have the eigenvalues, this is product of the eigenvalues. 2k is a even number. Even number of real terms, their product is less than 0. What does it mean? All of them cannot be negative, because even then it will be greater than 0. All of them cannot be positive, even they will be positive. So, there exist beta I such that and beta j such that beta I is positive and beta j is negative. Let me complete it here and continue from this point. So, from this point we will continue in the next lecture.